Every map of the solar system you have ever seen shows the same view, the planets arranged in a flat line, orbiting neatly around the sun, as if everything exists on a single level plane. That image is not wrong, but it is incomplete in a way that hides almost everything that matters. The solar system is not sitting flat inside the galaxy. It is tilted, angled sharply relative to the Milky Way, so that what lies above it and what lies below it point in completely different directions through space. Above, the environment opens outward into regions where the density of matter drops and the structure of the galaxy begins to thin. Below, the direction leads inward toward regions of higher density, stronger gravitational influence, and far more violent stellar activity. And surrounding all of it, in every direction, is a boundary so distant that no spacecraft has ever reached it. A spherical shell of debris and ice extending for distances measured not in billions of kilometers, but in light years. Beyond that shell, the sun's influence fades and the galaxy takes over. What looks like a simple flat system is actually layered in 3 dimensions, stretching upward and downward into environments that behave nothing alike. Those directions are not empty. They are pathways into regions shaped by ancient stellar explosions, dense molecular clouds, and structures so large they are still being mapped today. The solar system does not sit in isolation. It moves through a landscape that extends far beyond the familiar plane we are used to seeing. If space content like this is your thing, we've got plenty more. Subscribe and you'll have a new documentary waiting for you next time you need one. The story begins with a diagram that was never meant to show the full picture. Close your eyes for a moment and picture the solar system as you have always seen it. A calm, flat arrangement, planets circling the sun in a thin, orderly ring, everything aligned on a single level surface. It feels complete. It feels correct. But it is only a slice. That familiar image comes from something real. The planets do orbit within a shared plane called the ecliptic, a flattened disk shaped by the rotation of the early solar nebula, the cloud of gas and dust that formed the sun. This is why every diagram stretches outward horizontally, why the orbits appear so clean, so contained. The structure exists. It is not an illusion, but the sun does not hold its influence only along that thin disk. Its gravity reaches outward in all directions, forming a vast 3-dimensional domain that surrounds the planets completely, not just sideways, but upward and downward as well. Far beyond Neptune, extending roughly 2,000 times farther than its orbit, this invisible sphere continues, shaping objects we have never directly seen. So the flat diagram is not wrong, it is simply incomplete. To understand what surrounds us, we need 2 reference frames. The first is the ecliptic, the flat plane defined by the planets themselves. The second is the galactic plane, the immense disk of the Milky Way, where most of its stars, gas, and dust are concentrated. These 2 planes do not align. They intersect at an angle of about 63 degrees. That angle changes everything. Because of it, when we move above the solar system, we are not just rising out of a planetary disk. We are pointing away from the crowded structure of the galaxy itself, into regions where stars thin out and the environment becomes more diffuse. But when we move below, we are angled toward the denser interior of the Milky Way, toward regions where gravity is stronger, where stellar activity increases, and where the galactic core lies far in that direction. Above and below are not opposites in the usual sense. They are entirely different destinations. This single geometric fact reshapes the map. It tells us that the solar system is not resting flat inside the galaxy, but tilted sharply, embedded within a much larger structure that pulls differently depending on direction. Every object beyond the planets, every distant boundary, Every incoming visitor is influenced by this orientation, and so our path becomes clear. We move outward from the sun, passing through each layer that defines its reach, from the planetary plane into the surrounding sphere, and then beyond its outer limits into true interstellar space. From there, we follow the tilt itself, tracing the paths that lead upward into quieter regions and downward into more active ones until we reach the edges of what can be measured. What begins as a flat picture opens into depth. Far beneath the surface of the Pacific, long cylinders of mud were lifted slowly from the dark. Each layer recorded time. Each grain held a trace of the past. As scientists examined these cores in the 1990s, they noticed something that did not belong: a thin layer of iron, but not ordinary iron. It contained iron 60, a radioactive isotope, meaning a form of iron with an unstable nucleus that decays over time. On Earth, iron 60 does not form naturally in measurable amounts. It cannot be created by volcanic activity, ocean chemistry, or biological processes. Its presence required a source far beyond this planet. Only one environment produces it. Inside massive stars nearing the end of their lives, extreme temperatures and pressures fuse lighter elements into heavier ones, including iron 60. When such a star collapses, it explodes as a supernova, releasing its contents into space at tremendous speeds. The isotope is cast outward, drifting through interstellar space for millions of years. Eventually, some of it arrives here. Dating of the ocean layer placed its arrival between about 2.6 and 3.2 million years ago. In cosmic terms, this is recent, a brief moment. Yet the signal was clear, preserved in sediments undisturbed at the bottom of the sea. But the ocean was not the only place it appeared. The same isotope was later identified in lunar samples brought back during the Apollo missions, embedded in rock that had no atmosphere to shield it. It was found across multiple ocean basins, not confined to a single location. It was even detected in Antarctic ice cores, preserved within trapped cosmic ray particles. This was not local contamination, it was a global event. In 2016, researchers traced the likely origin. A nearby group of massive stars, known as the Scorpius-Centaurus OB association, had experienced a supernova during that same window. An OB association is a loose cluster of young hot stars, often short-lived and prone to violent endings. This one lies about 300 light-years away. At the time of the explosion, its position relative to us was not neutral. It sat partly above the galactic plane, aligned along the same tilted geometry that shapes our view of the sky. The material it expelled did not spread evenly in all directions. Some of it traveled along paths that intersected directly with the solar system, and it arrived, not as light alone, but as matter, physical debris from a dying star, settling onto the ocean floor, embedding itself into rock, leaving a measurable trace that we could one day uncover. But the event did not end with that layer. The same stellar group responsible for this signal has shaped the environment we move through even now. Its influence did not fade when the explosion ended. It expanded, evolved, and continues to define the space around us in ways that are only beginning to be mapped. The iron 60 is only the evidence, a quiet signature, proof that what happens beyond the solar system does not stay there. If we could step outside the solar system and look around, we would not see a uniform field of stars. The surrounding space would feel strangely hollow, as though something had swept it clean long ago. This region has a name. It is called the local bubble, a vast cavity in the interstellar medium, the thin mixture of gas and dust that fills the galaxy between stars. The cavity spans roughly 1,000 light-years across, extending in all directions around us. Within it, the density of matter is far lower than the galactic average. But this emptiness is not natural, it was carved out. Over the past 10 to 14 million years, a series of supernova explosions erupted in our stellar neighborhood, each one sending shock waves outward at thousands of kilometers per second. These expanding fronts collided with surrounding gas, heating it, pushing it away, and gradually excavating a hollow region in space. We are inside that hollow. The structure is not theoretical. It has been mapped using the distribution of nearby stars and the absorption of light by interstellar dust. In 2022, astronomers combined data from the Gaia Space Telescope with detailed infrared dust maps to reconstruct the local bubble in 3 dimensions with unprecedented precision. The result was clear. The solar system sits close to the center, surrounded by a shell of compressed gas and dust that outlines the bubble's boundary. That shell is not quiet. It is active, dense, and filled with the raw material for new stars. Nearly every region of star formation within 500 light years lies along this surface. The Taurus molecular cloud, the Perseus cloud, Ophiuchus, Lupus, Chameleon, each one a cold, dense accumulation of gas where gravity is pulling matter together to ignite new stars. These clouds did not form randomly. They were shaped and compressed by the same shock waves that cleared the interior. The source of those explosions traces back to a familiar origin, the Scorpius Centaurus OB Association, a nearby group of massive stars, lived fast and died violently, producing the sequence of supernovae that formed this cavity. The same stellar neighborhood that left traces in Earth's geological record also reshaped the structure of the space we occupy today. But the bubble is not uniform in every direction. Above the solar system, the cavity opens into a low-density channel known as the local chimney, a vertical corridor where gas becomes even more sparse, allowing hot material to flow outward toward the galactic halo. This creates a pathway into a quieter, more diffuse environment. Below the boundary behaves differently. There, the local bubble presses against another supernova remnant called Loop I, forming a region where two expanding cavities meet. The gas is denser, more turbulent, shaped by overlapping shock waves that have not yet settled. So the space around us is not balanced. It has direction. One path leads outward into thinning structure, the other into compression and activity. Both were created by the same ancient violence, but they evolved differently over time, and we remain suspended between them. You are not only orbiting the sun, you are moving inside something it is constantly pushing outward, an unseen flow that fills the space around every planet. It begins at the surface of the sun. There, charged particles break free from the outer atmosphere, the corona, and stream into space as the solar wind. This wind is not air. It is a plasma, meaning a gas so hot that its atoms have lost electrons, leaving a mixture of protons, electrons, and helium nuclei. These particles race outward at speeds between 400 and 800 kilometers per second. They do not stop. The flow expands in every direction, passing across planetary orbits, rising above and below the familiar plane, carrying the sun's magnetic field with it. Over distance, this continuous outflow inflates a vast region around the solar system, a bubble carved into the surrounding interstellar medium. This region is called the heliosphere. It is the domain where the sun's influence dominates, where its magnetic field and particle pressure outweigh the external forces of the galaxy. Inside it, conditions are shaped by the sun. Outside it, those conditions change. But the heliosphere is not symmetrical. As the solar system moves through the galaxy at about 26 kilometers per second, it meets resistance from the interstellar medium, the sparse gas and dust between stars. On the forward side, facing the direction of travel, the heliosphere is compressed. On the opposite side, it stretches into a long trailing region, a tail that extends far behind. The leading edge points toward the constellation Hercules. There, the boundary lies closer to the Sun. Behind us, the structure elongates, forming a vast magnetic wake that may reach beyond 1,000 astronomical units, where 1 astronomical unit is the average distance between Earth and the Sun. Above and below the ecliptic, the extension is more balanced. In those vertical directions, the heliosphere reaches outward to roughly 100 to 120 astronomical units before encountering the interstellar medium. Yet even this distance shifts over time. During periods of high solar activity, when eruptions and particle flows intensify, the pressure increases and the boundary expands outward. During quieter periods, it contracts. The edge is not fixed, but its role is constant. As the solar wind pushes outward, it deflects many incoming cosmic rays, high energy particles arriving from distant events across the galaxy. Without this shielding, far more of that radiation would penetrate the inner solar system, reaching Earth's atmosphere at much higher rates. In this way, the heliosphere acts as a protective layer, not solid, not visible, but effective. But its protection has limits. Beyond roughly 120 astronomical units, the Sun's influence weakens and the balance shifts. The particles, fields, and radiation of the galaxy begin to dominate. The space above and below that boundary is no longer shaped primarily by the Sun. It belongs to something larger. On a quiet day in late August 2012, a signal changed. It did not announce itself with light or sound, only with data, a subtle shift in the readings from a spacecraft that had been traveling outward for decades. That spacecraft was Voyager 1. Launched in 1977, it had spent 35 years moving away from the Sun, passing the outer planets, and continuing into regions no probe had ever reached. By the time it approached 121 astronomical units, something unusual began to happen. The solar wind faded. For decades, its instruments had measured a steady stream of charged particles flowing outward from the sunday. Then, suddenly, those particles dropped away. In their place, detectors registered an increase in cosmic rays, high-energy particles arriving from outside the solar system. The transition was abrupt. This boundary is called the heliopause, the point where the outward pressure of the solar wind is balanced by the pressure of the interstellar medium. It marks the outer edge of the heliosphere, the limit where the Sun's dominance gives way to the galaxy. But the crossing was not defined by distance alone. At the same moment, the magnetic field around the spacecraft shifted direction. Instead of aligning with the Sun's magnetic influence, it began to follow the broader magnetic field of the local interstellar environment. The spacecraft had entered a new regime, not empty space, but different space. 6 years later, in November 2018, Voyager 2 reached the same boundary. Its path was not identical. It approached from a direction roughly 48 degrees below the ecliptic, crossing at a distance of about 119 astronomical units. The differences mattered. Outside the heliopause, Voyager 2 measured a plasma density, the number of charged particles per unit volume, that was higher than what Voyager 1 had encountered. This confirmed that the interstellar medium is not uniform. It varies with direction, shaped by local conditions and past events. Voyager 2 carried one more advantage. Its plasma instrument, designed to directly measure the temperature and density of charged particles, was still functioning. In interstellar space, it recorded temperatures between 30,000 and 50,000 Kelvin. This was far hotter than expected for the surrounding region, suggesting that the local environment had been heated by ancient stellar activity, a lingering effect. Yet both spacecraft share a limitation. Neither is traveling along the true vertical paths defined earlier. They move through oblique angles, not directly above or below the ecliptic. The polar exits of the heliosphere, the directions that align with that tilted geometry, remain unvisited. We have not been there. What lies at those boundaries is inferred from models, not measured by instruments. The data we have is partial, drawn from specific trajectories through a complex structure that changes with direction. Still, the message is clear. The edge is real. It can be crossed, and beyond it, the solar system is no longer the dominant force shaping what surrounds us. Imagine standing at the very edge of the sun's influence, where its outward pressure fades and the surrounding galaxy presses in from all sides. Even here, the story is not finished. Something vast still surrounds us, extending far beyond any region we have directly explored. It is called the Oort Cloud. This structure begins at distances of roughly 2,000 astronomical units and may extend outward to 100,000 astronomical units, approaching 2 light-years from the Sunday. It forms a nearly spherical shell, enclosing the entire solar system rather than lying within any single plane. But no one has ever seen it. Not directly. Not once. There are no images of Oort Cloud objects in their native environment, no spacecraft observations, no telescopic detections of individual members at those distances. Its existence is inferred from motion, from patterns traced by objects that briefly enter the inner solar system before disappearing again. These are long-period comets. Unlike short-period comets, which orbit within the flattened disk of the planets, long-period comets arrive from all directions. Some descend from steep angles above the ecliptic. Others rise from below, approaching on trajectories that seem almost vertical. Their orbits are highly elongated, taking tens of thousands to millions of years to complete a single pass. This pattern led to a conclusion. In 1950, Dutch astronomer Jan Oort analyzed these trajectories and recognized that their distribution was uniform across the sky. They were not concentrated along any plane. The only explanation was a distant, spherical reservoir of icy bodies surrounding the solar system in every direction. A cloud without a center. Estimates suggest it contains between 100 billion and 2 trillion objects composed of ice, rock, and primordial material left over from the formation of the planets. These objects were not formed in place. They were scattered outward billions of years ago by gravitational interactions with the giant planets, flung into distant orbits where they remained. And they have stayed there, in deep cold, in near isolation. But the Oort Cloud is not protected. It exists fully exposed to the gravitational influence of the galaxy. The Milky Way exerts a subtle but persistent force known as the galactic tide, a slow stretching effect caused by the distribution of mass across the galactic disk. Passing stars contribute as well, their gravity nudging objects as they move through the stellar neighborhood. Even distant encounters matter. A star passing within 1 or 2 light-years can disturb thousands of these objects, altering their paths. Some are sent inward, beginning long journeys toward the Sunday. Others are pushed outward, drifting away into interstellar space, no longer bound at all. At the outer edge, the sun's grip is weak. There, even the gentle pull of the galaxy is enough to reshape orbits over millions of years. The boundary becomes uncertain, a gradual transition rather than a sharp line. Above and below, the structure continues uninterrupted. It forms the solar system's ceiling and its floor, a vast archive of frozen bodies suspended in all directions. Each one is a remnant from the earliest era, unchanged since the system formed 4.6 billion years ago. We have never seen them, but they are there. Picture the galaxy not as a backdrop, but as a force that is quietly acting on everything around us. Its presence is not distant, it is continuous, shaping motion even at the farthest edges of the solar system. The Milky Way contains between 200 and 400 billion stars. Alongside them exist vast reservoirs of gas, dust, and an unseen component called dark matter, a form of mass that reveals itself only through gravity. All of this contributes to a gravitational field that extends across the galaxy. But this field is not uniform. Because much of the galaxy's mass is arranged in a disk, its gravitational pull behaves in a specific way. It is strongest in the direction perpendicular to that disk, meaning straight above and straight below the galactic plane. Along the plane itself, the pull is more balanced and less pronounced. This difference creates what astronomers call the galactic tide. A tide is a differential force, meaning it pulls more strongly on one part of a system than another. In this case, the galaxy pulls differently on objects at various distances from the Sunday. The effect is subtle, but over long periods, it becomes significant. The outermost region feels it most. Objects in the distant cloud described earlier are only weakly bound to the Sunday. Their orbits are broad and slow, making them sensitive to even slight external forces. The galactic tide gradually alters these orbits, stretching and tilting them over tens of millions of years. It does not act suddenly. Instead, it shifts the shape of an orbit little by little, lowering the distance at which an object passes closest to the Sunday. Eventually, some of these objects are nudged onto paths that carry them inward, where they become visible as long-period comets. This process accounts for most of them. Models of orbital dynamics suggest that about 90% of long-period comets from the outer cloud are delivered by this slow gravitational influence rather than by random collisions or close encounters with passing stars. The effect is not evenly distributed. It is strongest on objects located far above and far below the planetary plane, where the vertical pull of the galaxy is most pronounced. In these regions, the structure is continually reshaped, with orbits evolving under the steady influence of the surrounding mass. But even this force changes over time. The solar system itself moves up and down through the galactic disk in a long cycle. When it passes closer to the midplane, where mass is more concentrated, the tidal effect becomes stronger. When it moves farther away, into less dense regions, the influence weakens. The rate at which comets are sent inward shifts with it. So, the galaxy is not passive. It is actively interacting with the outer solar system, reaching into its most distant regions through gravity alone. Over immense timescales, it rearranges trajectories, redirects objects, and occasionally sends them inward across vast distances. A quiet process, but persistent. Sometimes, without warning, a new light appears in the sky. It brightens over nights, grows a tail, and then slowly fades, slipping back into darkness as if it had never been there. But it has been somewhere. Every long-period comet that enters the inner solar system comes from far beyond the planetary region, arriving along steep, often vertical paths that cut across the familiar orbital plane. These objects originate in distant reservoirs, traveling for thousands or even millions of years before becoming visible. They carry history with them. Each one is a fragment of material preserved since the solar system formed about 4.6 billion years ago. Frozen in isolation, unchanged by sunlight or planetary interaction, they remain chemically primitive, retaining the conditions of their origin. When they approach the sun, that preservation ends. As heat increases, ices begin to sublimate, meaning they transform directly from solid to gas. This releases trapped compounds, forming a glowing coma around the nucleus. Its scale was immense. The nucleus was estimated to be about 60 kilometers across, far larger than most comets observed near Earth. As it warmed, it released a rich mixture of molecules, including water vapor, carbon monoxide, methanol, formaldehyde, and hydrogen cyanide. More complex chemistry emerged as well. Observations detected compounds related to glycine, an amino acid precursor, raising questions about how such molecules form in cold, distant environments. These findings supported a long-standing idea that comets may have delivered organic building blocks to early Earth, contributing to the chemistry that led to life. But not all messages are straightforward. In 2007, Comet McNaught displayed a dust tail unlike any seen before. When illuminated by sunlight, the tail revealed fine parallel bands, delicate structures arranged in striations that extended outward in precise patterns. These features have not been fully explained, though they may reflect variations in particle size or composition within the comet's material. Each comet adds detail. Isotopic ratios, which are the relative amounts of different forms of the same element, provide clues about temperature and environment during formation. Volatile compounds reveal how far from the sun the material originated. Organic molecules hint at the chemical pathways active in the early solar system. All of it arrives together. These objects are not just passing bodies, they are samples, delivered across vast distances, shaped by forces beyond the planetary region and guided inward over immense spans of time. They do not speak in words, but in composition. In October 2017, a faint point of light moved against the background stars in a way that did not match anything familiar. Its path was steep, its speed unusual, and its origin impossible to trace to any known region within the solar system. It was not bound to the Sunday. The object had arrived on a hyperbolic trajectory, meaning an open path that passes through once and does not return. Its velocity was too high to be explained by any gravitational interaction with the planets. It had come from outside. This object was named Oumuamua, a Hawaiian term meaning scout or messenger from afar. By the time it was discovered by the Pan-STARRS telescope in Hawaii, it had already passed its closest point to the sun and was moving away. Astronomers had only a short window to observe it before it faded into darkness. Even in that brief time, it revealed something strange. As it rotated, its brightness changed dramatically by a factor of about 10. This variation suggested an extreme shape. Either it was elongated, perhaps 10 times longer than it was wide, or it was flattened into a thin, broad form. Nothing like this had been observed among known asteroids or comets. Its origin direction added another clue. It entered the solar system from above the planetary plane, arriving from the general direction of the constellation Lyra. Its incoming velocity matched the motion of stars in the local neighborhood, indicating it had been traveling through interstellar space for an unknown length of time. But the most unusual feature appeared as it departed. Oumuamua accelerated slightly, moving faster than gravity alone could account for. This excess acceleration was measured repeatedly and confirmed through multiple observations. Yet there were no visible signs of outgassing, the release of gas that typically produces thrust in comets. No tail, no coma, The cause remains unresolved. In 2019, a second visitor was detected. This one was named Borisov after the amateur astronomer who discovered it. Unlike the first, Borisov behaved in a familiar way. As it approached the sun, it developed a visible coma and tail, driven by the sublimation of ice. Its composition could be studied in detail. Spectroscopic analysis, which breaks light into its component wavelengths, revealed chemical signatures similar to those found in comets native to our solar system. Water, carbon-based molecules, and other volatiles were present, suggesting that the processes forming icy bodies may be common across different star systems. But the contrast between the two objects remained. One familiar, one not. Together, they changed our understanding. They showed that material from other star systems can and does pass through our own, entering from above or below, crossing the planetary region, and leaving without returning. These encounters are brief, but they carry information about environments far beyond our reach. And they may not be rare. Statistical estimates based on detection rates suggest that at any given time there could be at least one interstellar object larger than 100 meters passing through the inner solar system. Most remain undetected, too faint or too distant to be noticed. They move quietly, unseen, out past the last familiar giant, where sunlight fades to a dim glow. The solar system begins to lose its neat structure. Orbits stretch, paths tilt, the geometry we expect starts to unravel. There is still order here. Between about 30 and 100 astronomical units lies a region known as the Kuiper Belt, a broad ring of icy bodies that follows the general plane of the planets. It is the source of many short-period comets, objects that return regularly on predictable paths shaped by gravitational interactions with Neptune. But just beyond that ring, the pattern breaks. The scattered disk emerges as a population of objects with orbits that are elongated, tilted, and often unstable over long timescales. These bodies were flung outward early in the solar system's history, accelerated by close encounters with Neptune, and sent onto trajectories that carry them far above and below the planetary plane. They do not stay confined. One of the largest known members is Eris, discovered in 2005. It currently resides at about 96 astronomical units from the Sun and follows an orbit tilted roughly 44 degrees relative to the ecliptic. Its size and distance played a role in redefining what we consider a planet, leading to the reclassification of Pluto. But even Eris fits within expectations. Its orbit can be explained by known gravitational processes shaped by interactions with Neptune during the early migration of the giant planets. It belongs to a system we understand. Then comes something different. In 2003, astronomers identified an object named Sedna. Its orbit did not match any known pattern. It does not approach the Sun closely enough to have been scattered by Neptune, yet it is far too close to be part of the distant spherical cloud. Its path is isolated. Sedna reaches a closest distance of about 76 astronomical units, already beyond Neptune's influence, and travels out to roughly 937 astronomical units at its farthest point. Completing one orbit takes about 11,400 years. No known mechanism produces this trajectory. Neptune cannot account for it. The inner planets are far too weak. The usual scattering processes do not apply. Sedna appears to have been placed where it is by something else, something not directly observed. Other objects share this behavior. In 2014, astronomers discovered an object designated 2012 VP, 113. Its orbit shows a similar pattern, with a closest approach near 80 astronomical units and an elongated path extending hundreds of astronomical units outward. There is a pattern emerging. The orbits of these distant objects appear aligned in ways that are difficult to explain through chance alone. Their orientation suggests they are being influenced, guided by a gravitational presence that remains unseen. But what could create such structure? One possibility is a passing star, long ago, disturbing the outer regions and leaving objects behind in unusual configurations. Another is the gradual influence of the galactic tide acting on an early distribution of material. But a third idea has gained attention. A distant, massive body. Something large enough to shape orbits, yet far enough away to remain hidden. The evidence is indirect, drawn from motion rather than observation. But it is persistent, and it points outward. The clues do not come from light. They come from motion, from distant objects tracing paths that seem to agree with one another in ways that should not happen by chance. In 2016, astronomers Konstantin Batygin and Mike Brown examined a group of extreme trans-Neptunian objects, bodies moving on distant, elongated orbits far beyond Neptune. 6 of them showed a striking pattern. Their orbital orientations were clustered, aligned in a narrow range of angles rather than scattered randomly. The odds were low. Statistical analysis suggested that such alignment had about a 1 in 14,000 chance of occurring naturally. Something was shaping these orbits, guiding them over long time scales into a shared configuration. The proposed explanation was simple in concept. A planet. Not one we have seen, but one whose gravity could account for the observed structure. This hypothetical world became known as Planet 9, a distant body influencing objects without revealing itself directly. Its predicted properties are specific. Models suggest a mass between 5 and 10 times that of Earth, orbiting at distances ranging from about 400 to 800 astronomical units. Its path would be highly elliptical, meaning stretched into a long oval and tilted between 15 and 25 degrees relative to the planetary plane. One orbit would take time. Estimates place its orbital period between 10,000 and 20,000 years, meaning it would spend centuries moving slowly across the sky, then drift even farther out, becoming almost impossible to detect. And detection is already difficult. At such distances, a planet of that size would reflect very little sunlight. It could be 1,000 times fainter than the faintest objects currently cataloged in that region. Even large telescopes would struggle to distinguish it from background noise, especially if it is currently near the farthest point of its orbit. But its position matters. The geometry of its orbit suggests it would spend much of its time above or below the ecliptic, moving through regions that have not been thoroughly surveyed. This reduces the chances of accidental discovery and requires targeted searches across vast areas of sky. Some searches have been conducted. Observations using the Subaru telescope in Hawaii, equipped with the Hyper-Suprime cam, have scanned portions of the predicted region without finding a clear candidate. But the coverage is incomplete, and the search space remains enormous. New data continues to emerge. In 2024, analysis from the Dark Energy Survey identified additional distant objects whose orbital properties align with the influence of a massive unseen body. The pattern persists, even as the sample grows. But the question remains open. Planet 9 has not been observed. Its existence is inferred, supported by models and patterns that could still have alternative explanations. The evidence points toward something but does not yet reveal it. And that uncertainty carries weight. It means that in the vast regions above and below the solar system, there could be a world larger than Earth, orbiting in darkness, shaping the structure of distant objects without ever reflecting enough light for us to see it. For now, it remains hidden. Our path through the galaxy is not a flat circle. It is a layered motion, one that carries us around the center while also lifting us above and dropping us below the galactic disk. We orbit at speed. The solar system travels around the galactic center at roughly 230 kilometers per second, completing one full circuit in about 225 to 250 million years. This duration is sometimes called a galactic year, and since its formation, the solar system has completed about 20 such orbits. But that motion is only part of the story. At the same time, we move vertically. The gravitational pull of the galaxy's mass, concentrated within its disk, draws the solar system toward the midplane. As we pass through, the pull reverses direction, slowing our motion and eventually drawing us back again. This creates an oscillation, a repeated up and down movement through the galactic plane, like a slow wave. The full cycle takes about 64 to 70 million years, meaning we cross the galactic plane approximately every 32 to 35 million years. At the highest points, we reach distances between 230 and 300 light years above or below the midplane before gravity pulls us back inward. We are not at the center of that motion now. Current estimates place the solar system between 56 and 80 light years above the galactic midplane, still moving upward. This direction leads away from the densest regions of the galaxy and toward the more diffuse halo that surrounds it. But this position will not last. As the oscillation continues, we will slow, stop, and begin to fall back toward the plane, repeating a cycle that has continued for billions of years. Each passage through the midplane brings different conditions. Density changes. Near the galactic plane, stars are more numerous, gas clouds are thicker, and dark matter may be more concentrated. Passing through these regions increases the likelihood of close stellar encounters and exposes the solar system to higher levels of cosmic radiation. The outer regions respond as well. The distant cloud of objects surrounding the solar system becomes more sensitive to gravitational disturbance during these crossings. The galactic tide strengthens, and the rate at which objects are nudged inward can increase. There may even be traces of this motion on Earth. In 1984, paleontologist David Raup and geologist Jack Sepkoski identified a pattern in the fossil record, suggesting a cycle of mass extinction events occurring roughly every 26 million years. Later analyses adjusted this timing and found partial alignment with the solar system's vertical oscillation. The connection remains uncertain. No direct causal link has been confirmed, but the possibility has been explored in multiple studies, suggesting that cosmic environment may influence conditions on Earth over geological timescales. Over its history, the solar system has crossed the galactic plane and returned many times. Each passage has carried it through a different region, under different conditions, within a galaxy that is itself evolving. The environment above and below is not fixed. It changes with our motion. The nearest stars are not fixed in place. They drift through the galaxy on their own paths, each following a separate orbit around the galactic center, slowly changing the pattern of our local neighborhood over time. Distances seem large. Within about 10 light years, there are roughly a dozen known stars and brown dwarfs, objects too small to sustain steady fusion. Extend that range to 50 light years, and the number rises into the hundreds. Each of these bodies is moving, sometimes toward us, sometimes away. Over long timescales, paths cross. A passing star does not need to enter the inner solar system to have an effect. The outer regions are loosely held, and even a distant encounter can alter them. When a star passes within 1 to 2 light years, it moves through the region occupied by distant icy objects, where the sun's gravitational hold is weakest. That is enough. The passing star exerts a gravitational pull that perturbs or slightly changes the orbits of those distant bodies. Most shifts are small, but some are enough to redirect objects inward. Over time, this can create what researchers call a comet shower, a period when more comets enter the inner solar system than usual. These events leave subtle traces. In 2015, astronomers confirmed that a system known as Schultz's star had passed within about zero point 0.8 light years of the Sun around 70,000 years ago. This distance places it well inside the outer boundary of the distant cloud of objects. It came quietly. Schultz's star is a faint binary system composed of a red dwarf and a smaller brown dwarf companion. At that distance and brightness, it would have appeared as a dim point of light, slowly moving across the sky, likely visible for a brief time without drawing attention. But its passage mattered. A study in 2018 examined the trajectories of 339 hyperbolic minor planets, objects moving on paths that will carry them out of the solar system. Their incoming directions showed a pattern that may be consistent with perturbations caused by that encounter. Not definitive, but suggestive. Future encounters are already known. Data from the Gaia Space Telescope, which measures stellar positions and motions with high precision, has identified a star called Gliese 710 as the most significant upcoming visitor. It is currently about 62 light-years away and moving toward us. Its path is well constrained. In approximately 1.29 million years, it is expected to pass within about 0.06 light-years of the Sunday. This is far closer than the previous encounter, deep within the distant outer regions where objects are only weakly bound. The effects could be substantial. Models suggest that such a passage may increase the rate of incoming long-period comets by up to a factor of 10, creating a prolonged period of increased activity lasting several million years. The direction matters as well. Given the orientation of the solar system, the influx would likely arrive from a specific region of the sky, shaped by the geometry of the encounter and the tilt of the system itself. The outer regions are not isolated. They are open to influence, shaped not only by the Sun and the galaxy, but also by the slow, steady passage of neighboring stars. If you turn your attention away from the crowded disk and follow the upward direction defined earlier, the surrounding structure begins to open. The density of matter drops, and the environment shifts into something quieter, more diffuse. The change is not gradual at first. Beyond the cavity we inhabit, the path above leads into a region known as the local chimney, a corridor of unusually low-density gas extending several hundred light-years upward from our position. It aligns with an opening in the surrounding structure, forming a channel that connects our local region to the larger galactic halo. This corridor was not guessed. It was identified through observations of neutral hydrogen, the most common form of gas in the galaxy, along with measurements of soft X-ray emission. In certain directions, above the galactic plane, astronomers found regions where the expected gas density was significantly lower than surrounding areas. Something had cleared it out. The local chimney represents one of these cleared pathways, shaped by past energetic events that displaced material and created a route through which gas can move more freely. It is not empty, but it is far less crowded than the regions within the galactic disk. And it is active. Hot gas from the interior of the surrounding cavity can rise through this channel, moving upward into the halo in a process known as a galactic fountain. This term describes a cycle in which gas heated by supernova explosions expands outward, escapes the disk, cools over time, and eventually falls back under gravity. A slow circulation. The local chimney provides a route for that motion, allowing energy and matter to flow between regions that would otherwise be more isolated. It is part of a larger system of vertical exchange that connects the dense disk to the extended halo. But this structure is not fixed. Over millions of years, the surrounding interstellar medium shifts, new stellar events occur, and existing cavities expand or collapse. The shape and extent of the local chimney evolve with these changes, adjusting as the galaxy itself continues to develop. Looking upward through this corridor, the environment continues to thin. The interstellar medium becomes increasingly sparse, with fewer atoms per cubic centimeter, and the distribution of stars changes as well. Younger, metal-rich stars become less common, replaced by older populations that formed earlier in the galaxy's history. These stars carry different signatures. They contain fewer heavy elements, reflecting a time when the galaxy had not yet been enriched by repeated generations of stellar evolution. Their presence marks a transition into a more ancient region where the conditions differ from those within the disk. The local chimney opens into that domain. It serves as a passage from a relatively active environment into one that is older, quieter, and less dense. Above, the structure of the galaxy fades, and the halo begins, extending outward into a vast region that surrounds the entire system. This upward path is not empty space. It is a route into a different kind of environment. Follow the upward path far enough, and the structure of the galaxy begins to dissolve into something broader, more diffuse, and far older than the regions below. The disk fades, and a different component emerges, one that surrounds the entire system. This is the galactic halo. It extends outward for distances reaching 300,000 light-years or more, forming a vast envelope around the Milky Way. Unlike the dense disk, where stars, gas, and dust are concentrated, the halo is sparse. Matter is spread thinly, and the environment is quieter. But it is not empty. Suspended within this region are globular clusters, dense, spherical collections of stars bound tightly by their own gravity. Each cluster contains hundreds of thousands to millions of stars, packed into a relatively small volume compared to their surroundings. They move differently. Globular clusters do not orbit within the galactic plane. Instead, they follow long, looping paths that carry them high above and far below the disk, tracing extended trajectories through the halo over billions of years. There are many. The Milky Way hosts between 150 and 200 known globular clusters. Among them, Omega Centauri stands out. It contains roughly 10 million stars and is visible to the naked eye from the southern hemisphere. Its structure suggests it may once have been the core of a smaller galaxy captured and stripped apart by the Milky Way's gravity. These clusters are ancient. The stars within them formed between 12 and 13 billion years ago, when the universe itself was only 1 to 2 billion years old. They predate the fully formed galactic disk, offering a glimpse into conditions that existed long before the solar system came into being. Their light travels slowly. Several of these clusters are positioned above our current location in the galaxy, and the light we see from them has been traveling for tens of thousands of years, crossing vast distances through the halo before reaching us. But clusters are only part of the structure. The halo also contains stellar streams, elongated ribbons of stars that were once part of globular clusters or smaller galaxies. Over time, tidal forces, meaning the stretching effect of gravity, pull these systems apart, dispersing their stars into extended arcs that wrap around the Milky Way. One example is the Sagittarius stream. It originates from the Sagittarius dwarf galaxy, a smaller system currently being disrupted as it orbits the Milky Way. The stream forms multiple loops around the galaxy, with portions passing above our position, tracing a path that reveals the ongoing process of galactic interaction. Beyond the stars lies another component. The circumgalactic medium surrounds the entire halo, composed of hot, diffuse plasma, a state of matter where particles are ionized and freely moving. This medium extends for hundreds of thousands of light years and may contain as much mass as all the visible stars combined. It is difficult to see. Optical telescopes detect little, but in X-ray wavelengths, the structure becomes more apparent, revealing a faint but extensive presence that fills the space between galaxies. Above the solar system, the galaxy opens into this vast region, an environment shaped not by density, but by age. Look upward from our position, and beyond the sparse halo, two faint shapes can be seen drifting against the darkness, visible without instruments from certain parts of Earth. They are not stars. They are entire galaxies. They hang in the sky, about 160,000 light-years away, in the direction defined as above relative to our tilted orientation, lie the large and small Magellanic Clouds. From the southern hemisphere, they appear as diffuse patches of light, detached from the main band of the Milky Way. Each is vast. The large Magellanic Cloud contains roughly 30 billion stars spread across an irregular structure about 14,000 light-years in diameter. The small Magellanic Cloud is smaller, with about 3 billion stars extending across roughly 7,000 light-years. Both are bound to us. They are satellite galaxies, gravitationally linked to the Milky Way, moving through its halo on extended orbits. Over time, these interactions have begun to reshape them, pulling material outward and altering their structure. The process is ongoing. Tidal forces, meaning the stretching effect caused by differences in gravitational pull, draw gas and stars from these galaxies, forming a long structure known as the Magellanic Stream. This stream arcs across the sky for about 180 degrees, stretching from above the galactic plane and curving partially below it. It is immense. The stream contains large amounts of hydrogen gas, enough to support star formation for billions of years if it is eventually absorbed into the Milky Way. It represents a transfer of material between galaxies, a slow, merging process that unfolds over immense timescales. But these galaxies are not quiet. On February 23, 1987, a star in the Large Magellanic Cloud ended its life in a supernova, an explosion marking the collapse of a massive star. This event, known as Supernova 1987A, became one of the most studied in modern astronomy. It was closer than any observed supernova since the early 17th century. Its proximity allowed detailed measurements across multiple wavelengths, providing insight into the physics of stellar collapse. Something else arrived first. 3 underground detectors on Earth recorded a burst of neutrinos, nearly massless particles produced in enormous quantities during the collapse of a star's core. These neutrinos were detected about 3 hours before the visible light reached Earth, confirming theoretical predictions about how supernovae unfold. The remnant continues to evolve. Astronomers have tracked its expansion for decades, observing shock waves moving through surrounding material. Inside, a neutron star is believed to have formed, an object of extreme density composed almost entirely of neutrons. In 2024, observations detected an ionized region consistent with that expectation. But the larger story continues. The Large Magellanic Cloud is gradually being drawn inward. Over the next 2.4 billion years, it is expected to merge with the Milky Way, adding its stars and gas to the larger system. Above us, entire galaxies are not distant abstractions. They are part of an ongoing process. In 2010, a pattern appeared where none was expected. Astronomers studying data from the Fermi Gamma Ray Space Telescope noticed two vast regions of high-energy emission extending above and below the center of the Milky Way. At first, it seemed like noise. The structures were too large, too symmetrical, and too sharply defined to fit known models. Instrument error was considered, but repeated analysis confirmed the signal. The features were real, embedded in the data, spanning an enormous vertical distance across the galaxy. They became known as the Fermi bubbles. Each bubble extends about 25,000 light-years from the galactic plane, forming a pair of structures that together reach roughly 50,000 light-years from top to bottom. They dwarf anything in the solar system and rival the scale of the galaxy's central regions. But they are not centered on us. Their origin lies near the galactic core, about 26,000 light-years away. From our position, they rise above and below the plane, forming part of the vertical architecture that defines the galaxy as a whole. Their boundaries are distinct. Unlike diffuse clouds, the edges of the Fermi bubbles are sharp, indicating a sudden transition between the interior and the surrounding medium. This suggests that the structures expanded rapidly, pushing into the halo at supersonic speeds and maintaining a defined front against the pressure of the surrounding gas. The cause is still debated. One possibility is a period of intense star formation near the galactic center between 6 and 9 million years ago. In such events, massive stars form in large numbers, live briefly, and end in supernova explosions, releasing energy that can drive large-scale outflows. Another explanation points inward. The central black hole, Sagittarius A star, may have experienced a phase of higher activity between 2 and 4 million years ago. During such a phase, it would have accreted large amounts of gas, converting gravitational energy into radiation and launching powerful jets or winds that expanded outward into the halo. Both scenarios involve immense energy. Either process could have injected enough power into the surrounding medium to inflate structures of this scale, shaping the environment far beyond the central region. The discovery did not end there. In 2020, observations from the eROSITA X-ray telescope revealed even larger features associated with the same region. These structures, known as the eROSITA bubbles, extend up to 45,000 light-years above and below the galactic plane and are visible across the entire sky in X-ray wavelengths. They expand the picture. Together, these observations show that the vertical dimension of the galaxy is not quiet or static. It carries the imprint of energetic events that have shaped the halo over millions of years, leaving behind structures that persist long after the initial activity has ended. From our position, these features are distant, but they define the environment we inhabit, part of a larger system where energy moves not only across the disk, but far above and below it. Shift your attention downward, along the direction defined by that tilted geometry, and the environment begins to change almost immediately. The path does not open outward. It leads inward, toward regions where matter gathers and activity increases. The first structure encountered lies just beyond our local surroundings. Below the solar system sits a large cavity known as Loop 1, another region shaped by past supernova explosions. Like the cavity we occupy, it was carved by expanding shock waves from massive stars, but its position places it along a different trajectory through the galaxy. The two regions meet. Between them lies a boundary that has been mapped through soft X-ray observations, revealing a thin, bright layer of compressed gas. This interface marks where the expanding shells of two ancient supernova remnants press against each other, forming a contact zone of increased density. It is not far away. Estimates place this boundary between 80 and 150 light-years below our current position, marking a transition from one cavity into another. The structure is dynamic, shaped by the continuing interaction of these expanding regions over millions of years. But the descent does not end there. Moving farther downward toward the galactic midplane, the interstellar medium becomes progressively denser. Gas clouds grow thicker, dust accumulates, and the environment shifts from sparse to crowded. The conditions here support active star formation. Molecular clouds appear. These are cold, dense regions composed primarily of molecular hydrogen, where gravity can overcome internal pressure and begin the process of star formation. Within them, new stars ignite, illuminating their surroundings and shaping the gas around them. Some regions become ionized. These are called H2 regions, areas where intense radiation from young, massive stars strips electrons from hydrogen atoms, creating glowing zones of energized gas. These regions are bright in certain wavelengths and mark sites of recent stellar birth. Dust plays a role as well. Dense lanes of interstellar dust absorb and scatter visible light, obscuring what lies beyond. For decades, these dust lanes limited our view of the galaxy's structure, leading early astronomers to underestimate its size and complexity. The deeper we look, the more crowded it becomes. Far below, near the galactic center, lies the central molecular zone, a region spanning about 700 light-years. It contains vast amounts of dense gas and is forming stars at a rate significantly higher than the average across the galaxy. Conditions intensify there. Radiation levels rise, gravitational interactions become more complex, and the processes of stellar birth and death occur more frequently. The environment is active, dynamic, and constantly evolving. This downward direction is not quiet. It leads toward concentration, toward regions where matter is abundant and energy is continually released. Compared to the sparse, ancient environment above, the contrast is clear. Density increases, activity rises, and the structure of the galaxy becomes more pronounced. At the end of this downward path, the direction does not simply continue into denser regions, it converges. Everything we have followed, every increase in density and activity, leads toward a single point deep within the galaxy. There is something there, not visible in the usual sense, but present through its influence, shaping the motion of stars and the structure of the surrounding region. This is Sagittarius A star, the supermassive black hole at the center of the Milky Way. Its scale is difficult to picture. It contains about 4.15 million times the mass of the Sun, compressed into a region comparable in size to the orbit of Mercury. Within that boundary lies a gravitational field so strong that nothing, not even light, can escape once it crosses a certain limit. That limit is called the event horizon. It marks the point beyond which escape is impossible, defining the edge of the black hole itself. But the object cannot be seen directly. Its presence is inferred from how nearby stars move under its influence. Those motions are precise. One star, known as S2, completes an orbit around Sagittarius A star every 16 years. At its closest approach, it reaches speeds of nearly 3% the speed of light, tracing a tight, elliptical path around something that emits no visible radiation. For decades, this was the evidence. Then came an image. In April 2022, the Event Horizon Telescope collaboration released the first direct observation of the black hole's shadow. Using a global network of radio telescopes, they captured a ring of glowing gas surrounding a dark central region, matching predictions from general relativity with remarkable accuracy. The structure was exactly where expected. But the black hole is not constantly active. At present, Sagittarius A star accretes gas at a relatively low rate, meaning it draws in matter slowly compared to more energetic galactic centers. The surrounding region is comparatively quiet, with only occasional bursts of activity. But it has not always been so. The large-scale structures described earlier, extending far above and below the galactic plane, suggest a past phase of significantly higher energy output. Those features remain as evidence of a more active period when the central region released vast amounts of energy into the surrounding halo. Even now, it can change. In 2019, astronomers observed a flare that briefly increased the brightness of Sagittarius A star by a factor of 75. The cause is not fully understood. It may have resulted from a clump of gas falling inward or an interaction with a nearby object. The system is dynamic. Conditions shift over time, influenced by the flow of matter and the complex environment surrounding the black hole. Even in a relatively quiet state, it remains the most extreme gravitational feature in the galaxy. And it lies in a specific direction, below and inward, along the path defined by the solar system's orientation, marking the endpoint of a gradient that began in sparse regions and moved steadily toward concentration. Above leads outward, but below leads here. If you remove every star, every cloud of gas, every grain of dust we have followed, something vast would still remain. It does not glow. It does not scatter light. Yet its gravity quietly holds the galaxy together. We are moving through it now. Astronomers call it dark matter, a form of mass that neither emits nor absorbs light, interacting primarily through gravity and shaping structures on scales far larger than anything visible. Its presence is inferred, not seen. When we measure how stars orbit the Milky Way, their speeds do not decrease with distance as expected. Instead, stars far from the center move just as quickly as those much closer in, a pattern known as the galactic rotation curve, meaning the graph of orbital speed versus distance. Visible matter cannot explain this. To account for those motions, there must be additional mass extending far beyond the luminous disk, surrounding it in all directions. This unseen component forms a halo, roughly spherical, stretching hundreds of thousands of light years above and below the galactic plane. We exist inside it. Estimates suggest this halo extends between 600,000 and 1 million light-years in radius, embedding the entire visible galaxy within a much larger gravitational structure. Most of the mass is here. In fact, about 85% of all matter in the universe belongs to this invisible category, outweighing ordinary matter by more than 5 to 1. Everything we see is the minority, but its influence is precise. The vertical motion we traced earlier, the gentle rise and fall of the solar system through the galactic plane, depends partly on the gravitational pull of this hidden mass. The timing of that oscillation, roughly 64 to 70 million years, provides clues about how dark matter is distributed. It shapes the rhythm. By comparing models of motion with observed positions, astronomers estimate how much unseen mass must lie above and below the disk, constraining its density without ever detecting it directly. Some ideas go further. A few models suggest that dark matter may not be entirely diffuse, proposing an additional thin concentration aligned with the galactic plane, sometimes called a dark disk, a flattened component that would increase density near the midplane. If such a structure exists, it could matter. Each passage through the galactic plane would bring the solar system through regions of slightly higher dark matter density, subtly altering gravitational conditions or increasing the chance of rare interactions with ordinary matter. But this remains uncertain. No direct detection has confirmed the composition of dark matter, and its fundamental nature is still unknown. Candidates range from undiscovered particles to compact objects formed in the early universe. The question remains open. What we do know is scale. Above and below the solar system, far beyond the visible structures we can map, this invisible mass dominates the architecture of the galaxy. It surrounds everything, and though we cannot see it, its presence is written into every motion, every orbit, every slow vertical drift we have followed through the Milky Way. Before any light reaches you, something faster and more silent has already arrived. Invisible particles pass through your body each second, crossing space without pause, carrying energy from distant, violent events scattered across the universe. We are constantly immersed in them. These are cosmic rays, high-energy particles made mostly of protons and atomic nuclei, moving at speeds approaching that of light and arriving from every direction, including directly above and below the tilted plane we have been following. They do not belong to one place. Some are born in supernova remnants, where expanding shock waves accelerate particles to enormous energies. Others emerge from pulsars, rotating neutron stars that fling charged matter outward through intense magnetic fields. But many come from farther away. Active galactic nuclei, the bright cores of distant galaxies powered by supermassive black holes, launch particles across intergalactic space. Some of the highest energy cosmic rays have traveled for billions of years before reaching this region. Their journey is uninterrupted. Within the boundary we crossed earlier, the solar wind offers partial protection. The heliosphere, that extended magnetic envelope, deflects a large fraction of lower energy cosmic rays, reducing their intensity before they reach the inner planets. But this shielding has limits. When spacecraft moved beyond that boundary, detectors recorded an immediate rise in particle flux, a direct confirmation that interstellar space contains a far denser background of energetic radiation. Out there, the exposure is constant. Yet even here, the most energetic particles pass through almost unaffected. These are ultra-high energy cosmic rays, defined as particles with energies exceeding 1 quintillion electron volts, an electron volt being the energy gained by a single electron in an electric field. Their energy is extreme. A single particle at 100 quintillion electron volts carries the kinetic energy of a thrown ball, compressed into a subatomic scale. When such a particle strikes Earth's atmosphere, it does not arrive alone for long. It multiplies instantly. The impact triggers an air shower, a cascading chain reaction where secondary particles spread outward, covering several square kilometers by the time they reach the surface. Vast detector arrays are needed to observe them. We have built them. In Argentina, the Pierre Auger Observatory spans 3,000 square kilometers, recording these rare events and tracing their incoming directions, some pointing toward regions above the galactic plane where distant extragalactic sources reside. Other signals arrive differently. Neutrinos, nearly massless particles that rarely interact with matter, pass through entire planets without stopping. To detect them, scientists have embedded thousands of sensors deep within Antarctic ice. They watch from below. The Ice Cube Observatory measures flashes of light produced when a neutrino finally collides with an atom, revealing its direction. Many of these detections correspond to particles that traveled through Earth, meaning they entered from the sky above the galaxy. One source stands out. In 2022, data confirmed that the galaxy NGC 1068, about 47 million light-years away, emits a steady stream of high-energy neutrinos. Those signals reached us intact. So from above and below, across distances almost impossible to imagine, energy continues to arrive, threading through space and through us, connecting this quiet region to the most distant and energetic processes in the universe. Imagine tracing a perfect circle around the galaxy, expecting symmetry at every point. But as we move outward in that mental map, the structure begins to bend, quietly at first, then unmistakably. The disk is not flat. Radio observations in the mid-20th century first revealed this distortion, using neutral hydrogen, meaning cold atomic gas, that emits at a specific radio wavelength to trace the galaxy far beyond visible stars. The signal curved. Instead of lying evenly along a single plane, the outer regions lifted upward on one side and dipped downward on the other, forming a warp that extends across tens of thousands of light-years. Later measurements refined it. In 2019, astronomers analyzed more than 1,300 Cepheid variable stars, stars whose brightness pulses at a rate tied directly to their intrinsic luminosity, allowing precise distance measurements across the galaxy. They mapped the shape in 3 dimensions. The result showed a pronounced asymmetric warp with displacements reaching nearly 5,000 light-years above or below the expected midplane in the outer disk. That is not a small deviation. It means that the directions we call above and below are not fixed across the galaxy, but shift depending on where you stand within its structure. Orientation becomes local. What appears as upward here may align with a completely different galactic region far from our position, reshaping how vertical motion connects to larger scales. But the warp is not frozen. It precesses, a slow rotation of the warped pattern itself around the galactic center, meaning the direction of maximum bending drifts over time, completing cycles that span hundreds of millions of years. The shape is evolving. The cause remains uncertain, but leading explanations include gravitational interactions with nearby satellite galaxies, particularly the Magellanic Clouds, and the distribution of dark matter within the galactic halo. Multiple forces may combine. Alongside this bending, another pattern emerges, less obvious but equally revealing. The disk is not smooth, but corrugated, a series of gentle ridges and troughs in stellar density that ripple outward from the central regions, like waves on water. These structures were identified in 2013 through large surveys of stellar positions and motions, revealing vertical oscillations layered across the disk itself. They carry a history. Simulations suggest these ripples may have been triggered by past encounters, possibly when the Sagittarius dwarf galaxy passed through the Milky Way's disk hundreds of millions of years ago, disturbing its equilibrium. The effects persist. So, as the solar system continues its orbit, and as it moves through its own vertical cycle, it does so within a structure that is neither flat nor static, but bending, shifting, and subtly vibrating across immense scales. But this changes perspective. The sky above and below us is not a permanent arrangement, but a temporary alignment within a dynamic system where position, direction, and environment evolve together over cosmic time. We are inside that motion, and the path we trace through it is shaped not only by gravity we can see, but by distortions that redefine the very geometry of the galaxy around us. Long before there was a sun to orbit, there was only a drifting cloud. It was cold, uneven, and quietly rotating, suspended within a larger region of gas where stars were forming in scattered pockets. Its direction was already set. This cloud, the solar nebula, meaning a rotating mass of gas and dust that collapses to form a star and planets, carried a subtle spin shaped by turbulence in its surroundings. That spin defined the future plane of planetary motion, not aligned with the galaxy. Measurements show that stellar systems form with orientations that appear almost random relative to the galactic disk, because local motions within their birth clouds dominate over any large-scale alignment. So our tilt emerged early. The angle we experience now, roughly 63 degrees between our orbital plane and the broader galaxy, reflects the exact orientation of that initial rotation, frozen into place as the cloud contracted. But something started the collapse. A cloud like this can drift for millions of years without forming a star, unless disturbed. One leading explanation suggests a nearby supernova provided that disturbance, sending a shock wave through space. It compressed the cloud. When such a wave passes through gas, it increases density and pressure, pushing regions beyond a threshold where gravity can take over, causing them to collapse inward and begin star formation. Evidence supports this. Meteorites formed in the earliest stages of the solar system contain traces of short-lived radioactive isotopes, elements that decay quickly and therefore must have been present at the moment of formation. They could not have formed here. Aluminium-26, an isotope of aluminium with a half-life of about 700,000 years, and iron-60, which persists for a few million years, are both produced inside massive stars and released during supernova explosions. They were injected directly. Their presence indicates that material from a dying star mixed into the forming solar nebula while these isotopes were still active, meaning the supernova occurred close in both time and distance. But the influence did not end there. As aluminium-26 decayed inside early planetesimals, meaning the small building blocks of planets, it released heat that caused these bodies to melt internally, allowing heavy elements like iron to sink and form cores. This shaped planetary structure. The layered interiors of rocky worlds, including Earth, trace part of their origin to this radioactive heating, linking their geology to an event that happened before the sun fully formed. But there is a deeper connection. The same nearby stellar environment that seeded those isotopes also contributed to the motion of the original cloud, adding velocity, turbulence, and possibly influencing its orientation at the moment collapse began. So the tilt is inherited. What we now call above and below, the directions that have guided this entire journey, were defined in that early moment, shaped by local conditions rather than galactic symmetry. A single event mattered. A star lived, evolved, and ended its life in a violent explosion, sending matter and momentum into its surroundings, altering a nearby cloud just enough to create a new system. And we are inside the result. The angle we look through, the structure we have followed, and even the internal heat that shaped the worlds around us all carry traces of that distant explosion, preserved across billions of years as a quiet, enduring imprint. If we hold still and look ahead instead of outward, the future begins to take shape as a set of quiet trajectories, each already underway, each carrying consequences that will unfold long after our current moment. Motion does not pause. Above and below, the surrounding region continues to evolve, and some of those changes are close enough in time that we can trace them with surprising precision. One approach is already known. In about 1.29 million years, a star called Gliese 710 will pass within roughly 0.06 light-years of the Sun, a distance placing it deep inside the outer reaches of the distant reservoir we considered earlier. It will not collide, but its gravity will matter. Moving through that region, the star will disturb countless loosely bound objects, altering their paths and sending a fraction inward over extended timescales. The response will be delayed. Comets nudged during the encounter may take hundreds of thousands to millions of years to reach the inner system, creating a prolonged increase in arrivals rather than a sudden burst. The sky will slowly change. At the same time, our position relative to the galaxy continues its gradual shift. The solar system is still moving upward, away from the denser regions below, heading toward a maximum height that will be reached in roughly 30 million years. Then it will reverse. Gravity will draw it back downward, beginning another passage through the galactic midplane, continuing a cycle that has repeated many times across geological history. But the surroundings are not identical each time. Large-scale structures evolve, and material continues to move through the galaxy. Streams of gas stripped from neighboring systems are slowly drifting inward, altering the distribution of matter above and below. These changes take longer. Over billions of years, that incoming material may contribute to new star formation, reshaping regions of the disk and altering the broader environment through which the solar system travels. But even larger motions are underway. Another galaxy is approaching. The Andromeda Galaxy is moving toward the Milky Way at about 110 kilometers per second, and in roughly 4.5 billion years, the two systems will begin to merge. The structure will not survive intact. During that process, the familiar disk will be disrupted, the halo stirred, and the clear distinction between above and below will be transformed into a more complex, merged configuration. Our reference frame will change. Even closer in time, the Sun itself continues its own evolution. It remains stable now, but over the next 5 billion years, it will exhaust the hydrogen fuel in its core and begin expanding. Its influence will grow. As it becomes a red giant, its outer layers will extend far outward, altering the extent of its surrounding region and affecting distant objects that have remained largely undisturbed. But this phase is temporary. Eventually, the Sun will shed those outer layers and collapse into a dense remnant, leaving behind a field of debris and a population of distant objects no longer tightly bound. They will drift. Some will escape entirely, moving into interstellar space, while others may be captured by passing stars, becoming part of new systems formed far from here. But all of this is already set in motion. The future above and below is not empty or uncertain. It is structured, measurable, and unfolding, shaped by paths that were defined long before we began to notice them. The next shift in our understanding will not come from where we go, but from how clearly we can see. Instruments now being completed will change the resolution of this entire vertical story. They will widen the view. In Chile, a new observatory is beginning a survey unlike any attempted before. The Vera C. Rubin Observatory will scan the visible sky every few nights, building a time-based record across multiple wavelengths. It will not take single snapshots. Instead, it will watch the sky change, detecting motion, faint objects, and brief events that current surveys often miss. This includes distant bodies moving slowly above and below the planetary plane. Many new objects will appear. Hundreds of trans-Neptunian objects are expected to be identified, along with candidates for the inner regions of the distant spherical reservoir, objects too faint or too slow to detect with previous methods. But timing matters. Interstellar visitors passing through the system may be discovered earlier in their approach, allowing longer observation windows and more precise measurements of their composition and motion. Another telescope will look differently. The Nancy Grace Roman Space Telescope, planned for launch later in this decade, will observe in infrared light, meaning wavelengths longer than visible light, that reveal cold, dim objects otherwise hidden. It will see what is dark. With a field of view far larger than earlier space telescopes, it can detect faint, distant bodies in the outer system, including those far above and below the ecliptic that emit little visible light. Cold worlds will emerge. Meanwhile, on Earth, a different kind of instrument is taking shape across two continents: the Square Kilometer Array, a vast network of radio antennas, will map neutral hydrogen, the most common form of atomic gas. This gas traces structure. By observing its distribution with unprecedented sensitivity, the array will reveal the three-dimensional architecture of the surrounding region, including the extended features that connect local space to the larger galactic environment. Details will sharpen. Structures previously inferred, such as low-density corridors and boundary layers, will be mapped with clarity, showing how gas moves and interacts above and below the galactic disk. But direct sampling is also considered. A proposed mission known as the Interstellar Probe would travel far beyond the current boundary reached by earlier spacecraft, moving toward distances approaching 1,000 astronomical units over several decades. It would measure directly. Instruments aboard would record the density, composition, magnetic field, and dust content of the medium outside the solar influence, providing ground truth for models built from remote observations. The direction could matter. If aligned with the vertical axis, such a mission would explore regions never directly sampled, offering the first in situ data from the true above or below pathways. But observations are already advancing. The James Webb Space Telescope continues to analyze incoming comets in detail, measuring their chemical makeup with precision, revealing the preserved material from distant regions. Each comet carries history. Their compositions reflect conditions from the early system, allowing us to compare models with actual samples delivered from far beyond the planetary region. So, the picture will refine, not through a single discovery, but through a steady accumulation of detail, each instrument adding depth until the space above and below is no longer inferred, but mapped, measured, and understood with increasing clarity. Lay out everything we have followed, then remove the certainty from each piece, and what remains is not a finished map, but a framework filled with gaps. There are many. Some are small, details waiting for refinement, but others are vast regions where we have only indirect evidence shaped by inference rather than direct observation. Consider the boundary again. The regions directly above and below the planetary plane, the true polar exits of the solar influence, have never been visited by any spacecraft. No instrument has sampled those directions in place. We rely on models. Their structure, their particle flow, and their interaction with the surrounding medium are constructed from theory and sideways measurements, not from direct traversal. The outer reservoir remains unseen. The distant spherical population we infer from comet orbits has never been imaged where it resides. Not one object has been observed in its original position, suspended in that far region. Its properties are uncertain. Estimates of its population range from tens of billions to trillions of bodies. Its total mass, its exact shape, and the fraction of those objects containing complex organic material remain open questions. But uncertainty extends closer. The proposed distant planet, suggested to explain orbital clustering, has not been detected. Its existence is debated, and the observed patterns may reflect observational bias rather than an unseen, massive body. We do not yet know. Evidence preserved in geological layers confirms that material from a stellar explosion reached this planet, but the identity of that event, its exact distance, and whether similar episodes repeat over time remain unresolved. The connection is incomplete. An object that passed through this region recently displayed behavior that has not been fully explained. Its motion deviated from simple gravitational expectations without clear evidence of conventional causes. The mechanism is unknown. Beyond all of this lies the largest uncertainty. Most of the mass shaping the galaxy remains undetected directly. Dark matter, which dominates the gravitational structure above and below, has never been observed interacting in a controlled experiment. Its nature is still hidden. We can trace its effects through motion and structure, but its composition, its distribution in fine detail, and its possible interactions with ordinary matter are not yet understood. But this is the deeper point. The system we inhabit is not fully mapped or fully characterized. It is embedded in a broader environment that we have only begun to measure, with many of its defining features still inferred rather than confirmed. The map is partial, and that incompleteness is not a flaw, but a condition of where we stand, early in the process of understanding a structure that extends far beyond direct reach. So when you consider what lies above and below, you are not looking into a finished picture, but into an active frontier, where the most significant discoveries are likely still waiting, shaped by regions we have yet to observe and questions we have only begun to ask. Begin with the models we carry without noticing. You picture a ring, a calm arrangement circling a central star, everything moving in a shared direction across a flattened stage that feels complete. It seems sufficient, but the moment we allow a second axis to matter, that picture begins to open, and the system you imagined reveals connections extending far beyond its edges. The structure lifts. That vertical direction is not empty extension. It is the pathway through which outside forces reach inward, shaping motion, delivering material, and altering conditions over immense spans of time. Influence arrives there. Subtle gravitational gradients from the larger stellar system act most strongly away from the flat plane, gently reshaping distant orbits until objects begin long inward journeys that cross every inner region. Those journeys are slow, yet they connect distant storage to inner activity, linking regions separated by tens of thousands of astronomical units through gradual, persistent change. But the same direction also serves as an entry. Objects formed around other stars pass through from angles that ignore the familiar plane, crossing through the system on paths that reveal a shared galactic environment rather than an isolated one. They do not align. Their trajectories carry the signature of distant origins, reminding us that what surrounds this system is not uniform emptiness, but a populated and dynamic medium. The vertical axis also records time. Far from the central plane, distant reservoirs preserve material that has remained largely unchanged since early formation, maintaining chemical and structural records that predate most transformations closer in. They endure quietly, closer to the broader galactic environment. That same direction leads into regions where the density of matter and energy changes, where star formation, radiation fields, and gravitational complexity increase in ways that contrast sharply with the calm interior. Conditions shift. One direction moves toward older populations and thinner distributions, the other toward concentration, interaction, and continual renewal, each defined by different histories unfolding across the same galaxy. But the system does not stay fixed between them. It moves. Over tens of millions of years, its position rises and falls relative to the broader structure, changing its exposure to surrounding material, radiation, and gravitational influence. The environment evolves. At certain points, the surrounding density increases, encounters become more likely, and distant objects are more easily perturbed, subtly altering what enters the inner regions. At other times, conditions relax. This motion means that what lies above and below is not constant, but part of a shifting context that redefines the system's surroundings across deep time. So the simple picture dissolves. What once appeared as a flat, contained arrangement becomes a cross-section of a larger structure, embedded within layers that extend far beyond the paths of the planets. And within that structure, we find ourselves positioned between contrasting regimes, not isolated, but suspended, between different expressions of the same galaxy, each direction carrying its own history, its own conditions, and its own influence on everything that unfolds within. Consider the timeline that carries us to this moment. The system we inhabit formed about 4.6 billion years ago, while the universe itself stretches back roughly 13.8 billion years, placing our origin well into a later chapter. We arrive mid-story. The material that built this system was not created here. It was inherited, assembled from debris shaped by earlier generations of stars that lived, fused elements, and ended in explosive dispersal. Those endings mattered. Inside massive stars, lighter elements were fused into heavier ones, carbon from helium, oxygen from carbon, iron from successive stages of fusion, each step requiring extreme pressure and temperature. Nothing survives unchanged. When those stars reached their limits, they expelled these elements into surrounding space, mixing them into the wider medium that drifts between stellar systems. That medium became the source. From it, new clouds formed, collapsed, and spun into disks, eventually producing stars and planets, each carrying forward a chemical record of earlier stellar lives. But that process did not stop. Events occurring millions of years after formation still left measurable traces, showing that the system remains connected to the same cycle that created it. Material still arrives. Isotopes found in geological layers demonstrate that nearby stellar explosions continued to deposit fresh elements long after planets settled into stable orbits, linking past formation to ongoing change. These are not isolated incidents. They are part of a continuous exchange, where matter moves through space, enters gravitational systems, and becomes incorporated into new structures over time. Look outward again. At the farthest reaches of the system, distant objects preserve early material in cold storage, maintaining compositions that reflect conditions present during formation. They wait silently, but beyond them lies the broader environment, filled with gas, dust, radiation, and gravitational influence, all participating in the same long cycle of transformation. Nothing stands apart. Even the central star, stable as it appears, contains within its core the products of earlier stellar generations, continuing the process of fusion that will one day return its own material to that wider medium. The cycle continues, but the scale expands further still, because this process is not unique to one system. It occurs throughout the galaxy, repeated across hundreds of billions of stars, each contributing to the same exchange. Every system participates. The elements that make up oceans, atmosphere, and living structures have passed through multiple environments before arriving here, shaped by events that occurred far from this location. You carry that history. The atoms within you were once part of distant stellar interiors, later dispersed, then gathered again into new forms, eventually becoming part of a world capable of reflecting on its origin. This is the connection. What surrounds the system above and below is not separate from it, but part of a continuous process that links formation, evolution, and transformation across vast spans of time and space. And within that process, we are not observers standing outside. We are participants formed from it, shaped by it, and still connected to everything that continues beyond the boundaries we have traced. Try to redraw the picture in your mind, but do not begin with the planets. Instead, begin with a volume. You are inside a region that extends far beyond any orbit you have seen, a layered structure where distance, direction, and influence stretch outward in every dimension at once. The familiar plane is only a slice. Around that slice, extending outward for nearly 2 light years, lies a vast spherical reservoir of distant objects, each one loosely bound, each one responding slowly to forces that originate far beyond the central star. They drift in silence. Their orbits are not arranged in a ring, but scattered across a 3-dimensional envelope, forming a boundary that marks the fading edge of local gravitational control. But that boundary is not the end. Beyond it, the environment changes character. As the outward pressure from the central star gives way to the broader conditions of the surrounding medium, where particles, magnetic fields, and radiation are governed by the galaxy itself. The transition is real. Measurements taken at that boundary show a shift in particle populations and field orientations, confirming that the influence of the local star yields to a larger structure that continues in every direction. Look upward from there. Density decreases, stellar populations thin, and the medium opens into extended regions where older stars trace long paths and where the distribution of matter becomes increasingly diffuse. It becomes quieter. At greater distances, entire satellite systems remain suspended, gravitationally bound yet separate, their material slowly interacting with the larger system over immense spans of time. They remain visible, but look in the opposite direction. As you move downward relative to that same reference, the environment becomes denser, with increasing concentrations of gas and dust, regions where new stars ignite and older ones end their lives, returning material back into circulation. Activity rises. Farther along that direction, gravitational complexity increases, and trajectories bend more strongly under the influence of concentrated mass. Motion becomes intricate, but the system you are within does not remain fixed between these conditions. It moves gradually. Over tens of millions of years, its position shifts relative to the surrounding structure, altering the balance between these environments, changing exposure to radiation, density, and external perturbations. Conditions evolve. This means the place you occupy is not defined by a static setting, but by a path through a larger system, one that continuously redefines what surrounds it. But the most important shift is conceptual. The diagram you once imagined as complete is revealed as incomplete, not because it was incorrect, but because it lacked depth, lacking the dimension where most interactions with the wider galaxy occur. The hidden axis matters. When you include it, the system transforms from an isolated arrangement into a connected region within a vast, structured environment, one that extends far beyond any simple representation. And within that environment, you exist at a precise location, neither central nor separate, but embedded within layers of structure that connect local motion to galactic scale processes. This is home, not a flat arrangement, but a position within a three-dimensional system shaped by forces that extend far above and far below and carried along a path that links every part of it into a single, continuous whole.